Don't get embarrassed. All right, so section 2.2 is the derivative function. So what we're going to do today is find out how we can use the derivative and apply that to our functions. Close the door. Okay, so the definition for derivative, f prime of x. Make sure that you remember that yesterday when we did this, we're using the limiting process here, and the way this is read is f prime. Okay, and again, we're just picking up with the difference quotient. Review of honors pre-calc. Okay, so the derivative is what we use to study rates of change. Okay, so to find the equation of the tangent line to a curve at a point, okay, there's 3 steps. So the first thing you're going to need to know is what the point is on the curve. So step 1 is really telling you to find the point x comma y. The second is telling you to evaluate your derivative at that value of x. Remember that that is the slope of the tangent line. We did that yesterday. So we're just going to connect this to yesterday. The limit as h goes to 0. And then the third one is going to remind you to put this in y equals mx plus b, or you could do point slope form. Okay, so just algebra 1. All right, so find the derivative with respect to x of f of x equals x squared, our favorite calc curve ever, and use it to write the equation of the line. So the first thing we need to do is find f of x plus h, which is, and then we want to subtract those and take the limit as h goes to 0. So x squared minus plus 2xh plus h squared minus x squared all over h. Remember that this should all go away. And now I want to simplify. Cancel out the 0. And now I can let h go to 0. And the answer is 2x. So this is the derivative of f with respect to x. It's 2x. Now step 2. Oh, it would help if I did step 1, huh? So, you're laughing at me. 2 squared is equal to 4. So the point x comma y is equal to 2 comma 4. I should have done this first. My bad. So here's step 2. So now I need to evaluate this at that x value. And now I'm just going to use my point slope formula, which is y minus 4 equals the slope m at x minus 2. And we stop. We don't have to go any further. Done. Okay, find the derivative with respect to x of the function f of x. So again, we're going to do the difference quotient. Notice the parentheses and this minus sign. So we want to distribute that minus sign to everything. And this is a cubed. So we're going to get 1x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h. And I'm starting to use shortcuts now because f of x would be subtracted from this. So I'm going to minus x cubed minus a negative x. That's all over h. Gone, gone. And so now I want to factor an h out of my 4 remaining terms. So h leaves me 3x squared plus 3xh plus h squared minus 1. And all the while, I need to be remembering the limit as h goes to 0. Now I can let h go to 0. And the final answer for f prime of x is equal to 3x squared minus 1. So that's going to be the equation of the derivative. And I can actually plug that in, any values of x to that, and plot the curve. This is just a curve, and I'm hoping that you can tell me what that is. Parabola, vertex at 0, 1, 0, -1. Remember, it shifted down 1. So let's take a look over here at our picture, and there we are. Okay, so keep in mind that the original curve was a cubic. That's the original curve. And at any point along that curve, for any values of x, I can generate a t-chart. I don't want to, but I could. And so if I plugged in 0, I'd get -1. If I plugged in 1, I'd get 2. If I plugged in -1, I'd get 2. And you can see that those points are here. Over 1, up 2, -1, up 2. See? So these 3 points, and now there you go. Okay? You didn't actually have to graph it. There's the picture. But that's what you would do. Okay? Also, strongly encourage you to use your calculator. Please, please, please use your calculator. Find the derivative with respect to x of f of x equals the square root of x. So the first thing we do, f of x plus h. And remember, this is our definition of derivative of, and I'm not writing this every time because I'm lazy. I don't want to. And remember, we are now calling that f prime of x. And as long as we're in general terms, this needs to be general. Any x, arbitrary. Okay, so it's going to be the square root of x plus h minus the square root of x all over h. Whenever I see radicals, I need to multiply by the conjugate, because that's the way I can undo those square roots. And if I do that, the top gets real pretty, because it's going to be x plus h minus x. And on the bottom, again, I just said it, I'm lazy. I don't want to FOIL that out or anything, so I'm just going to leave it like that. On top, x minus x goes away, h over h. So I'm left with this, the limit, as h goes to 0, of 1 over x plus h plus the square root of x. And as I simplify that, I'm going to get the square root 1 over 2 square root of x, because that's going to go to 0. So, taking a look at the picture, we have 2 pictures to look at. The first picture is the actual graph of y equals the square root of x, and the second picture is the graph of the derivative. So, this is pretty close to a vertical line. Then what's happening to the slope as we move along the curve? It's getting closer and closer to, yep, you guessed it, 0 without actually being there. Okay. Part B, find the slope of the tangent line at x equals 9, which means now I want to take this and I want to evaluate it at x equals 9. So 1 over 2 times the square root of 9 is 1 over 2 times 3, which is 1/6. And now we want to say, look at the limit of the derivative as x goes to 0. So what we really want to do is want to take a look at this and say what's happening to that as x goes to 0. And as x goes to 0, from the right, that's the only place we can look at it, is from the right. As x goes to 0, that number is getting infinitely small, which means this is going to infinity. Okay? So that's what we're looking at. As this number gets infinitely large, now we look as it gets super, super big, then it's going to go to 0. Look at where this is going as x goes to infinity. Look at where this is going as x goes to 0. Okay? All right, so instantaneous velocity, this is specific use of the definition for the derivative, okay? Because now we're talking about just velocity, and we want the instantaneous velocity. So the first thing we need to do is just to find the velocity function. What they're really asking us is to take the derivative of this. So f prime of t is equal to the instantaneous velocity by definition. And so what we want to do, this is important. We're talking here about the s sub t function. So we're talking about a position function. So the derivative of a position function, is the instantaneous velocity. So if we let the limit as h goes to 0 of f of t plus h minus f of t all over h, and we want h to go to 0. So again, we're doing a lot of algebra. Anywhere I see a t, I want to plug in t plus h. Okay, so a little bit of distributive property. Oh. So I did some math in my head, FOIL, and then multiplied by -2. And so from that, I would subtract 1 minus 5t minus plus 2t squared. Gone, gone, gone. The original function is gone. So now we're left with gone, gone, gone. So remember, that's all over h. So we have 5. We're going to factor out the h from the 3 remaining terms. 5 minus 4t minus 2h all over h. Gone. Now I can let the limit of h go to 0. Notice I'm not writing it. I'm in limit as h goes to 0. And the answer is 5 minus 4t. Now that's just the derivative at any t. At any t. Okay? I'm specifically told to find out this. Done. I'm not asked to evaluate. Okay, differentiability. This probably is one of the most important concepts. And here's the deal. This is really just continuity with one more step. So to refresh your memory, in order to be continuous, the limit as x approaches c for any function has to exist. Okay, it has to exist. Okay, the second thing is that f of c must be defined. And the third and final step is that the limit as x approaches that c is actually equal to the function value at that point. So these were the 3 rules for continuity. And now, in addition to that, we're going to tack on one more rule. For differentiability, all of those are true. And there's one more step. The derivative of x, which remember, the limit as h goes to 0, f of x plus h minus f of x all over h. The general derivative must be actually equal to the derivative when evaluated at that point. Okay? So that actually has to equal whatever it is we're talking about. Okay? So whatever your function is, okay, that has to be true. And that has to be true coming in from the right and the left. Okay? They have to be approaching the same value. So right off the bat, piecewise functions are going to pose a problem at that vertex. Piecewise functions are going to pose an issue. So your book uses words like corner and cusp. And so a corner would be where you change. So if I draw in a slope here, this slope looks like it's positive. This slope looks like it's negative. They're never going to reach the same value. So this one is not differentiable. Now, coming in here, this slope is becoming undefined. Vertical tangencies or an undefined slope, not differentiable. Okay, here, a slope coming in this way and a slope coming in this way. That is never going to be differentiable at that point. It may be differentiable over here, but it is not going to be differentiable at that point. Okay? Same thing here. We have issues. And same thing here. We have issues. Okay? So, in order to be differentiable, the slope coming into the point has got to be approaching that slope that's coming in from the other side. And your book uses the formal definition that when you evaluate it at some point, that's any point I want, it has to be equal to the general derivative. So, looking at the graph of y equals f of x, is this absolute value of x. It's going to look something like this, correct? Yes, Ms. Collins. So, 0 is a point of concern because this line is going to follow the rule coming in, and then once it hits 0, it's going to follow a different rule coming out. So now, using the definition here, it says, hey, let's use the definition and figure out what's happening. So I'll do this in red, and now I'm going to pick it up and move it over here. We'll do the red side first. So x plus h minus x all over h. X minus x goes away. What's h over h? 1. Okay, so now we look at it from the left side. We're doing the same thing. I'll use blue even. Notice I didn't even need the limit, so negative, plug in the x plus h, minus the negative x. So negative x minus h, 2 negatives make a positive, all over h, gone, gone. Negative h divided by h is equal to negative 1. Negative 1 and 1 are not equal, therefore that function is not differentiable at x equals 0. Means I cannot take the derivative there. I can show you here, that's what's happening. In the blue side, you're constantly negative 1. On the red side, you're constantly at positive 1. Those are never going to be equal at x equals 0, and therefore not differentiable. Okay, so between differentiability and continuity, the relationship is, and this is like a geometry, if you are reading in a problem that a function is differentiable, then you can assume that it's continuous. By definition, it is. However, if it says it's continuous, that does not necessarily mean that it's differentiable. Okay? In words. All right, you're going to do the quick check exercises. Remember, the answers are on page 155. If there is anything in the notes that you did not get, please, please, please make a note to yourself so that tomorrow within the first 20 minutes we can answer those questions. The second thing I would recommend, whenever you are doing this and you have a function, if you don't know what that function looks like, pull out your graphing calculator and graph it so that you can see what it looks like. It's always beneficial if you can see a picture that goes along with the words. Okay? Good luck.